For the beam that's shown here, which has simply supported boundary conditions, we have a concentrated load there at B. We have a linearly increasing line load, which extends there from location C to D. Our goal here is to find the magnitude and location for the single force equivalent for that pair of loads, and then secondly, you then use that in order to find the reactions on the beam acting there at supports A and D. We're going to do this in two parts. Let's call the first system 1. We're going to first replace system 1 by a second system, which has the line load replaced by its single force equivalents, or at least a pair of those. So what I'm saying here is we have this simply supported beam. The loads that we have applied are F, and then we have the line load. The constant part of that line load, its equivalent is going to be the force per length across there, like that. That's a W, and it has a length there of 3D. And then if I take the triangular load, its resultant is going to be half of the base times the height. The base here is 3D, and the height is W. And what we want to do there, once we get through, then is make that equivalent to what is the single force equivalent of those combined loads. So the third system is going to be a simply supported beam with a equivalent load there of R at some distance there of D. Our goal there is to find both D and R. So again, this is 2 and this is 3. We've already made system 1 equivalent to 2 by replacing that line load by its two parts there of 3WD and 1/2 of 3WD. If I make this X and Y, and if I sum forces on 3 in the Y direction, to make that equivalent to 2, I sum forces in Y on 2. So what I have here is a minus R for 3, and then for 2 I've got the minus F. I have a minus 3WD and minus 3/2 of WD, like that. So what I have when I get through is the resultant force R then is equal to 9/2 WD plus F. So that's R. And I will choose some point, in this case A. I'll find the moments about A for system 3, and to make 2 equivalent to 3, I also have to have the moments about that same point balanced out between the two. So for 3, that moment is going to be R times the moment arm of D. That's going to be in the minus K. That's equal to minus F times small d. That's the location of the concentrated force. The first resultant there of the constant part of that line load, that was 3WD. It has a moment arm of 5D over 2. And then the triangular part, that's going to be, and I think I wrote down the wrong SIGN sign here, that should be a minus. And then for the triangular part, which had the magnitude force there of 3/2 WD, it has a moment arm of 4D. That would be this D plus that D plus 2/3. We know that this resultant here is going to be 2/3 of 3D there, so that's going to be 2D across there. So that's let me just make sure I've got that part right there. So yeah, that's a 2D. It's a 2D here. So overall, that's going to be a moment arm of 4D, and it's going to be in the minus K. So for this, I see that RD is equal to, um, what do we have there, 27 over 2WD plus F with the D factored out. And so therefore the location of that single force equivalent, D, is going to be the 27 over 2WD plus F divided by the R. The R we said was equal to 9/2 WD plus F. And that ratio, that dimensionless ratio, gets multiplied by the dimension given in the problem there of D. So this defines the magnitude of the single force equivalent. This tells you the location. For B, we're wanting to now solve for reactions through equilibrium. So we draw the complete free body diagram now. So we have our, from system 3, we have the resultant force there of R. We have got AY and DY. These are the reactions at the supports there of A and D. Doing a summation of moments about A, I've got minus R times D, this is distance there, capital D, and the dy that has a moment arm of 5D. It's in the plus K. So from this, I can get that dy then is equal to 1/5 R times D divided by D. And so based on my number there for, or my equation above there for RD, it's going to be 27 over 2 WD plus F divided by 5, so I'll just multiply that by 1/5. My summation of forces in Y, that's going to be minus R plus AY plus DY. And I've already found dy, so from here I can calculate AY, and AY in the end will be equal to 9/5 WD plus 4/5 times F. So that's the reaction at the pin joint there at A, and this is the reaction there at support at D. So what did we do here? In terms of equivalency, what we want to do is replace the line load with and the concentrated force F with a single force equivalent. We do that in 2 steps. We replace the line load by 2 forces, one due to the constant, that's W times 3D, and then we replace the triangular part by its resultant, which is 1/2 times W times 3D. And with that, we're able to find the resultant here of R. We'll find the location of that through the moment balance between systems 3 and 2. And then for equilibrium, we do our usual thing of drawing the overall free body diagram that includes all the reactions. And then from that, we calculate for the reactions at A and D by using the equilibrium equations of moment about point A and the summation of forces in Y.